All right, hello. We are Group S, the Lazy Susan Group. I'm Chris Costanza.
I'm Nick Grapperhouse.
Phil Iris.
Luke Casera.
So I'm going to start a little bit and talk about our motivation for the project. First of all, this is the Not So Lazy Susan. So our motivation for this project was primarily to simplify the small family to medium-sized family dining experience. We all come from small to medium-sized families and have experience with spills, root interruptions, reaching, all things that can happen during the course of a meal. And our main motivation throughout this whole process was to produce a mechanical centerpiece that prevents or reduces the possibility of those things occurring. So for our market research, we had three primary options that we were considering. The first was a nursing home environment. Applying this to that environment in a way that it would serve food or pills or any necessary medication, etc., to elderly people in a nursing home. Second was a elementary school environment. Small children could be used as some type of game or like food distribution, snack distribution system. Ultimately, those two markets were ruled out due to being ineffective cost-wise. For the elderly, it wouldn't be personal enough for them to use. They like to interact with human beings and not with some machine that would distribute their food to them. And for children, it might not be easy enough for them to use with a motorized system to achieve the goals we wanted to in that market. So we settled on a small family dining experience. Like I said, we are aiming to reduce the risk of spills, reaching, root interruptions, anything that can displace the personal experience of a small family meal environment. So our solution is this. As I said, this is the Not So Lazy Susan. As you can see, it rotates. It's designed to rotate to whatever user requires the food. It's designed to hold plates on each of these four mechanisms. Not this one because it's housing the motor and such, but utensils, plates, anything that is necessary. One drawer is motorized to translate out, the other two are not. This is our working prototype, and to talk a little bit more about it, I'm going to throw it over to Nick.
All right, so I'm going to go through the risk assessment here. We have three significant impact risks, and the first is tipping and spilling. That was the first thing we had to kind of deal with. And we're going to be putting large amounts of food or drink on each of these plates, and we have to make sure that when they're fully translated, they do not tip. So two ways we've managed this risk is we've made this base, as you can see underneath here. It's very wide. And then another way is we've added weight to the central region of this to try to keep it from tipping. And then another significant impact risk would be electronic failure. We're going to go through this a little more in depth later, but we have an Arduino and a motor and some other electrical components that if any of those fail, then our electronic translation fails. One way we've managed this is we have plenty of backups, and we've made sure we secured the wiring. And then a mechanical failure, that's the last significant impact here, and this mainly is in the coupling between the motor shaft and the threaded rod. We will show you an up-close picture of that earlier, but essentially we've dealt with this by creating a set screw to hold the rod to the shaft, and then also we have extra we have extra threaded rods in case something would happen. For engineering analysis, we decided to do the L bracket, which is right here, as you can see, it's right here and here on these pieces, and then a U bracket, which is attached to the bottom of this plate. We chose these two pieces because they support all the weight as the food is translated outward, and we wanted to make sure that there would be no distortion or any sort of displacement when these were translated outward. And then finally, moving to our budget, we started with a budget of $386, and currently we are $36 under budget. Now I'm going to pass it over to Phil.
So I'm going to talk about our main performance goals. So the first things we were really worried about was we didn't want it to be too heavy, we didn't want it to be too bulky and be in the way more than it would actually help your family dining experience. So right now, the whole thing weighs probably about 12 pounds. is what we guess. So that's not too bad, easily moved. And then as far as bulky, right now it's about 17 inches by 17 inches as a whole device, which is about the size of a large pizza. So you're gonna put that in the middle of your table anyways. And then we wanted it to rotate, and we want each drawer to translate 8 inches out, which we have been able to do with the drawer slides. And then we wanted motorized translation, which we figured out was going to be too expensive to do on every drawer, so we did it on just one with a lead screw and a motor and a nut, which you will see when we do our prototype demo at the end of this presentation. And finally, we wanted our drawers to be able to support a max of 5 pounds in the center of each plate when it's fully extended without tipping or motor failure, any sort of thing, with a safety factor of 2, so we tested at 10 pounds. And then now I'm going to talk about upgrades for our prototype and out of scope things that we would like to do. So first of all, we would like to try to make it a little bit more compact. So that would be maybe reevaluating our spacing. We could probably take another inch or 2 out of the height. Right now it's about 6 inches tall, which is actually kind of perfect as far as being out of the way of your plate and silverware. And maybe reevaluating material, see if we can find something lighter, cheaper, more efficient. We would also like to add sides to this so it's aesthetically pleasing and you don't see all the mechanical underparts. And then as you'll see in the prototype demo, we did not reach our translation goal of translating out in 6 seconds. So another goal would be to get it to translate out faster to the user so they're not waiting for their food an overly long amount of time. And then we would like to add limit switches to each end of the lead screw and maybe integrate a phone app so you could play maybe a trivia game at dinner with your family and whoever wins gets their food first. Essentially, it would be making a robot out of it where it could rotate, motorized, translate to different dimension tables, and you could control it all with an app from your phone. So that would be long term. And now I'll pass over to Luke.
Okay, so I'm going to talk a little bit about the circuit design and Arduino controls. So what we, our big idea here was to have the plate translate out similar to like what a garage door would translate out like. So you'd have an infrared sensor that you would down press to go out, and then it would reach its max translation and then come back in when you tell it to. So the way we were going to do that was have an Arduino control with infrared control sensors, 2 limit switches, a potentiometer for control of the rate of translation, and a power supply. So what we're using right now is a low torque or a high torque, low RPM motor. The envelope here required that we used a smaller motor, so this is what we came up with. You can also see the coupling here. It's directly attached to the lead screw and secured with the set screw. And then this washer's here so that, and that's where a limit switch would go ideally in the future to tell when the plate is in its stowed position. So in the future we would want to have a higher RPM motor, and we would want to have a motor on each translating plate, which might involve some interference issues in the center. And then we would want to have independent infrared controls for each motor. So that concludes our video introduction of our project. And we'll actually do a quick demo here. Show how it translates. It's a little bit slow, as we mentioned. So like we said, come back. All right, thank you very much.
Thank you.